Right now, light is streaming past you at nearly 670 million miles per hour, filling the space around you without pause or effort. Nothing in the universe can overtake it. No rocket, no particle, no object made of matter has ever managed to cross this boundary. For a long time, scientists believed this was simply a curious property of light itself. That light happened to be extraordinarily fast. But in the 20th century, physicist Richard Feynman helped reveal something far more unsettling. The speed of light is not merely a limit for light, it is the ultimate limit for cause and effect. It is the fastest rate at which the universe can transmit information, the speed at which reality updates from one moment to the next. Every interaction in nature obeys this rule. Every signal between atoms, every electrical impulse in your nervous system, every thought forming quietly in your brain, nothing can happen faster than this universal pace. And if that limit were ever broken, even in principle, the structure of reality would begin to unravel. Past and future would lose their meaning. Cause could precede effect. Order would collapse into contradiction. To understand why this speed limit exists and why it is so deeply woven into the fabric of space-time itself, we need to travel backward, not just through space, but through history. So allow your body to relax. Let your breathing slow and let your attention drift gently into the past. In the year 1638, Galileo Galilei climbed a quiet hillside outside Florence, carrying nothing more than a lantern and an impossible question. He wanted to measure the speed of light. His plan was deceptively simple. An assistant waited on a distant hill holding an identical lantern. Galileo would uncover his light. The instant his assistant saw the flash, he would uncover his own. When Galileo saw the return signal, he would measure the delay. Distance divided by time. Speed revealed, the logic was sound, the execution was careful, but the result was frustratingly empty. No matter how far apart the lanterns were placed, the return flash appeared immediate. There was no measurable delay. Light seemed to cross the landscape instantaneously. Galileo repeated the experiment again and again. He increased the distance. He refined the timing. He chose assistants with faster reactions. Still, the same result. Light appeared to arrive with no detectable travel time at all. Galileo reached a cautious conclusion. Either light traveled infinitely fast, or it moved so quickly that human senses were simply incapable of measuring its speed across earthly distances. He suspected the second answer was correct, but he lacked the tools to prove it. The failure was not Galileo's reasoning, it was the scale of the experiment. Light moves at roughly 300,000 kilometers per second in a vacuum. At that speed, it crosses a single meter in a few billionths of a second. Human reaction times, by contrast, are measured in tenths of a second. Galileo was attempting to measure a delay millions of times smaller than the limits of human perception. The signal vanished into the noise before it could ever be seen. To reveal light's true speed, the universe itself would have to provide a much larger measuring stick, one that stretched not across hills and valleys, but across the vast distances of space. That opportunity arrived decades later, not on Earth, but in the shadow of a distant planet. In 1672, a young Danish astronomer named Ole Romer arrived at the Paris Observatory. His task seemed routine: track the motion of Jupiter's moon Io as it slipped into and out of the giant planet's shadow. Astronomers treated these eclipses as a cosmic clock. Io disappeared on schedule. Io re-emerged on schedule. At least it was supposed to. But as Romer watched month after month, a subtle irregularity began to emerge. The eclipses were not perfectly consistent. Sometimes they occurred earlier than predicted. Sometimes they were delayed. The discrepancy was small, but it was persistent, and it followed a pattern tied not to Jupiter, but to Earth's own motion through space. Romer realized he was not observing a flaw in the clock. He was watching the finite speed of light reveal itself for the first time. And with that realization, the universe quietly admitted that light was fast, but not infinite, and that its speed carried consequences far deeper than anyone had imagined. As Romer continued his observations, the timing of Io's eclipses followed a quiet but unmistakable rhythm. Across the year, the events drifted forward and backward in time with remarkable regularity. When Earth's orbit carried it closer to Jupiter, the eclipses appeared earlier than predicted. When Earth moved to the far side of its orbit, increasing the distance between the two planets, the eclipses arrived late. The total discrepancy grew to about 22 minutes over the full width of Earth's orbit around the Sun. At first, many astronomers dismissed this drift. They blamed imperfect calculations. Perhaps Io's orbit was slightly irregular. Perhaps Jupiter's immense gravity caused subtle variations that existing models could not capture. Romer considered these possibilities carefully. Then he set them aside. The pattern was too precise, too smooth, too perfectly synchronized with Earth's changing distance from Jupiter. In 1676, Romer proposed a revolutionary explanation. The eclipses themselves were not early or late at all. They were occurring exactly when they should. What changed was the time it took their light to reach Earth. When Earth was closer, the light had a shorter distance to travel and arrived but sooner. When Earth was farther away, the light needed more time to cross the expanding gap. Light, Romer realized, did not arrive instantly. It traveled at a finite speed. Using the diameter of Earth's orbit and the accumulated delay, Romer calculated that speed. His estimate was about 220,000 kilometers per second. By modern standards, the number was not perfect. It was roughly a quarter lower than the accepted value today. The size of Earth's orbit was not yet known precisely. His timing instruments, though careful, were limited, but none of that diminished the achievement. For the first time in human history, someone had demonstrated that light moves at a measurable velocity. That information does not arrive instantaneously, that the universe operates with built-in delays, woven quietly into its structure. This realization carried consequences far beyond astronomy. If light takes time to travel, then distance becomes time. To look outward is to look backward. The sun we see is not the sun as it exists now, but as it was 8 minutes ago. The stars are frozen snapshots of ancient moments. The universe reveals itself not as a single present, but as a layered tapestry of pasts. Romer's discovery also raised a deeper mystery. Light was incredibly fast, yet it was not infinite. Why should nature choose this particular speed? Why not faster or slower? What property of reality fixes this number so precisely? These questions would echo through physics for the next 2 centuries. As instruments improved, scientists refined Romer's result. In 1728, James Bradley discovered stellar aberration, a subtle shift in the apparent positions of stars caused by Earth's motion through space. This effect depended directly on the ratio between Earth's orbital speed and the speed of light, allowing Bradley to calculate light's velocity to within 1% of the modern value. Then, in 1849, Hippolyte Fizeau achieved the first successful measurement entirely on Earth. He used a rapidly rotating toothed wheel. A beam of light passed through a gap between the teeth, traveled to a distant mirror, and returned. By adjusting the wheel's speed until the returning light was blocked by the next tooth, Fizeau could calculate how long the journey took. Light, once thought instantaneous, had finally been timed by human hands. Yet, even as the measurements grew more precise, the deeper question remained unanswered. Why does light move at this speed, and why does nothing else ever manage to exceed it? As Romer continued to watch the skies, a subtle pattern began to reveal itself. The eclipses of Io did not drift randomly. They followed a quiet, almost musical rhythm that repeated itself year after year. When Earth's orbit carried it closer to Jupiter, the eclipses appeared slightly ahead of schedule. Months later, as Earth moved to the opposite side of its orbit and the distance between the two planets increased, the same eclipses arrived late. Across the full width of Earth's journey around the Sun, the discrepancy grew to nearly 22 minutes. At first, this strange timing was easy to dismiss. Astronomers blamed imperfect calculations. Perhaps Io's orbit was not perfectly regular. Perhaps Jupiter's immense gravity caused subtle variations no one had yet accounted for. Romer examined these explanations carefully, then he rejected them. The pattern was too clean, too consistent, and too precisely tied to Earth's changing distance from Jupiter. Chance could not explain it. In 1676, Romer offered a bold new idea. The eclipses themselves were not early or late at all. They were happening exactly when they should. What changed was the journey the light had to make to reach Earth. When Earth was closer to Jupiter, the light had less distance to cross and arrived sooner. When Earth was farther away, the same light needed more time to bridge the expanding gap. Light, Romer realized, does not arrive instantly. It travels at a finite speed. Using the diameter of Earth's orbit and the accumulated delay, he calculated that speed to be about 220,000 kilometers per second. By modern standards, the number was not exact. The true size of Earth's orbit was not yet known, and timing instruments were still crude. But the importance of the result went far beyond precision. For the first time in history, light had been shown to move at a measurable velocity. Information did not leap across the universe instantaneously. Distance carried delay, built quietly into the fabric of reality. This realization transformed astronomy, and far more than astronomy. If light takes time to travel, then distance becomes time. To look outward is to look backward. The sun we see is the sun as it was 8 minutes ago. The stars are ancient memories frozen in light. The universe reveals itself not as a single present moment, but as a layered archive of past events, each arriving at Earth on its own schedule. Romer's discovery also opened a deeper mystery. Light was astonishingly fast, yet clearly limited. Why should nature choose this particular speed? Why not faster or slower? What hidden structure of reality fixes this number so precisely? These questions lingered for centuries. As technology advanced, scientists refined Romer's work. In 1728, James Bradley discovered stellar aberration, a tiny shift in the apparent positions of stars caused by Earth's motion through space. From this effect, he calculated the speed of light to within 1% of the value we accept today. Then, in 1849, Hippolyte Fizeau brought the measurement down to Earth itself. Using a rapidly rotating toothed wheel, he sent a beam of light through a narrow gap, reflected it from a distant mirror, and caught it on its return. By adjusting the wheel's speed until the returning light was blocked by the next tooth, Fizeau measured the time of the journey directly. Light, once believed instantaneous, had finally been timed by human hands. And yet, even as the measurements grew more precise, the deeper question remained. Why does light move at this speed, and why does nothing in the universe ever manage to go faster when the wheel rotated at exactly the right speed? Something remarkable happened. The returning beam of light no longer slipped through the gap. It was blocked by the next tooth. By knowing how fast the wheel was spinning and how far the light had traveled to the mirror and back, the speed of light could finally be calculated with striking accuracy. A year later, in 1850, Léon Foucault refined the technique even further. He replaced the toothed wheel with a rotating mirror, allowing much finer control and far greater precision. His results closely matched those obtained from astronomical observations, confirming something profound. Light moved at the same speed, whether it crossed a laboratory or spanned the solar system. Later still, Albert Michelson devoted his life to pushing this precision to its absolute limit. Through meticulous refinement of rotating mirror experiments, he measured the speed of light with unprecedented accuracy, eventually earning a Nobel Prize in part for this work. By the end of the 19th century, physicists had converged on a single value. Light traveled at approximately 299,792 kilometers per second in a vacuum. The uncertainty had shrunk to mere parts per million, and something curious began to emerge. This number appeared everywhere, in Maxwell's equations, in electromagnetic theory, always the same, always exact. Scientists began to suspect that this was not merely a property of light itself. It seemed to reflect something deeper about the structure of reality. At the time, light was understood as a wave, and waves by definition require a medium. Sound waves need air, ocean waves need water. So light waves, physicists reasoned, must also travel through something. They called this invisible substance the luminiferous ether. The ether was imagined as a strange cosmic medium filling all of space, flowing between planets and stars. It had to be incredibly rigid to support waves moving at immense speeds, yet perfectly transparent, offering no resistance as Earth hurtled through it. If such an ether existed, Earth's motion should reveal it. As our planet orbits the Sun at about 30 kilometers per second, it should plow through this ether like a ship cutting through calm water. Light traveling in the direction of Earth's motion should be slightly slowed. Light traveling against it should be slightly sped up. Light moving perpendicular should remain unchanged. This subtle difference, known as the ether wind, should be measurable. The predicted effect was tiny, only about 1 part in 10,000. But by the late 19th century, experimental precision had reached the level where such a shift could be detected. The test would become legendary. Albert Michelson, already famous for his obsession with precision, joined forces with chemist Edward Morley. Together in 1887, they built the most sensitive optical instrument the world had ever seen. Its purpose was simple: detect Earth's motion through the ether. The Michelson-Morley interferometer split a beam of light into two perpendicular paths using a half-silvered mirror. One beam traveled parallel to Earth's motion through space. The other traveled at right angles to it. Both beams reflected off mirrors and returned to recombine. If the ether wind affected their speeds differently, the returning waves would interfere, producing a shifting pattern of light and dark bands. To eliminate vibrations, Michelson and Morley mounted the entire apparatus on a massive stone slab floating in a pool of mercury. The device could rotate smoothly, allowing them to test every possible direction. If the ether existed, the pattern would shift. They waited and waited. Nothing happened. This careful design allowed the entire experiment to rotate smoothly, free from vibrations that could corrupt the delicate optics. Michelson and Morley could point their instrument in any direction relative to Earth's motion and watch for the slightest change. Their confidence was high. The sensitivity of the interferometer exceeded what was required by a wide margin. If an ether wind existed at the predicted strength, the interference fringes would shift clearly and unmistakably. They repeated the measurements again and again, at different times of day, in different seasons of the year. As Earth changed direction in its orbit and swept through space at varying angles. And every time, the result was the same: nothing. The interference pattern refused to move, no matter how the apparatus was oriented, no matter when the measurements were taken. Light traveled at exactly the same speed in every direction. There was no trace of an ether wind, because there was no ether at all. This single result sent shockwaves through physics. Light was undeniably a wave, and waves were supposed to require a medium, yet the medium that light was thought to travel through simply did not exist. Something was deeply wrong. For years, physicists tried to save the old picture. Some proposed that Earth somehow dragged the ether along with it, eliminating relative motion near the surface. Others suggested that objects moving through the ether physically contracted in the direction of motion, precisely canceling the expected differences in light speed. These ideas could be made to work mathematically, but they felt artificial, like patches sewn onto a theory that no longer fit reality. The true resolution came from an unexpected place, not from a famous laboratory, not from a senior professor, but from a 26-year-old patent clerk in Bern, Switzerland. Albert Einstein had been thinking about light since he was a teenager. One question in particular had never left him. What would happen if you could chase a beam of light? If you could move alongside it at the same speed, what would you see? Would the wave freeze in place? Would electric and magnetic fields hang motionless in space, oscillating but never advancing? According to Maxwell's equations, this was impossible. Electromagnetic waves were not allowed to stand still. They had one speed and one speed only. A frozen light wave would break the very equations that had successfully explained every known electromagnetic phenomenon. Einstein faced a choice. He could assume Maxwell's equations were incomplete, or he could take them seriously even if their implications shattered common sense. He chose the second path. Light always travels at the same speed, not because of a mysterious medium, not because of the nature of photons alone, but because of how space and time themselves are structured. In 1905, Einstein published a paper titled On the Electrodynamics of Moving Bodies. It appeared quietly in Annalen der Physik, 30 pages, no citations, written not from a university, but from a patent office, and yet it would change reality. The paper opened with two statements so simple they sounded almost trivial, so innocent, and so devastating. Einstein began with two principles so simple they seemed almost obvious. First, the laws of physics are the same for all observers who move at a constant speed. Whether you are drifting quietly through space or riding smoothly on a train, the rules of nature do not change. Gravity, electricity, motion all behave the same way in every inertial frame. Second, the speed of light in empty space is the same for everyone, no matter how fast you are moving, no matter whether you chase the light, run away from it, or stand completely still. This is not an approximation. It is not a limit of measurement. It is an exact statement about reality. At first, these ideas sound harmless. Of course, physics should work the same everywhere. Of course, a fundamental constant should truly be constant. But when both statements are true, at the same time, the universe becomes very strange. Imagine standing still as a beam of light passes by you. You measure its speed as 299,792 kilometers per second. Now imagine a friend racing toward that same beam at half the speed of light. Classical physics says the speeds should add together. Your friend should measure the light rushing toward them faster than you do. Einstein said this never happens. Your friend still measures exactly the same speed, 299,792 kilometers per second. Now your friend turns around and flees from the light at half light speed. Classical intuition says the light should struggle to catch up, creeping forward more slowly. Einstein said no again. The light still arrives at exactly the same speed, the same number, every time, for every observer. This seems impossible. How can one beam of light move at the same speed relative to people moving differently? Something must change. What changes is not the light. What changes are space and time themselves. Einstein showed that space and time are not separate, rigid backgrounds where events unfold. They are woven together into a single structure called space-time. And your motion through space changes how you experience time. To protect the constancy of light speed, the universe adjusts the flow of time for each observer. This leads to time dilation. Clocks in motion tick more slowly than clocks at rest. Not because of mechanical failure, not because of perception. Time itself flows differently. At everyday speeds, the effect is so small we never notice it. An airplane flying across the Earth experiences time dilation, but the difference is only a few trillionths of a second. You would need to fly non-stop for thousands of years to lose even 1 second. But as speed increases, the effect grows. At 90% of the speed of light, time slows dramatically. For every year that passes on Earth, only about 5 months pass for the traveler. The faster you move, the more extreme the difference becomes. This behavior is described by a simple mathematical factor physicists call gamma. It depends only on your speed relative to light. When you are at rest, gamma equals 1. Time flows normally. As your speed increases, gamma grows larger. Time stretches. Moments expand. And as velocity approaches the speed of light, gamma rises without bound. At the limit, gamma becomes infinite. Time stops. Light does not slow down to accommodate you. Instead, time bends. Space reshapes itself. The universe preserves its speed limit not by restricting light, but by reshaping reality around anything that tries to chase it. A photon moving at the speed of light experiences no passage of time at all. From the photon's own perspective, the moment it is created and the moment it is absorbed are the same instant. Billions of years may pass in our universe. Galaxies may form and fade. Civilizations may rise and fall. Yet for the photon, the journey is timeless. Distance without duration. Motion without time. This strange fact explains something fundamental. Why light can move at the ultimate speed while anything with mass never can. Photons have no rest mass. They are not pushed up to light speed through acceleration. They are born already moving at that speed, and they cannot exist in any other state. A photon cannot slow down. If it somehow did, it would no longer be a photon at all. It would simply vanish from reality. Light is not just fast, it is different. Everything else in the universe carries mass, and mass binds objects to slower paths through space-time. Time dilation has a partner equally strange and equally real: length contraction. Objects in motion shrink along the direction they are moving, not because they are physically crushed, not because of visual distortion. Space itself contracts. A ruler rushing past you at high speed is genuinely shorter than an identical ruler at rest. And the faster it moves, the shorter it becomes. At 90% of the speed of light, lengths shrink to less than half their original size along the direction of motion. As velocity increases, this contraction intensifies approaching an extreme limit near light speed. Time dilation and length contraction are not separate effects. They are two sides of the same adjustment. Together, they preserve the cosmic rule. No matter how fast you move, light always measures at the same speed. When you chase a beam of light, your clock slows down. Your measuring rods shorten. You record distances differently. You record durations differently. But the ratio of distance to time, which we call speed, remains unchanged. This precise balancing act is described by mathematical relationships known as the Lorentz transformations. These equations translate measurements between observers moving at different velocities. They were first discovered by Hendrik Lorentz while attempting to explain the failure of the ether theory. Lorentz believed the equations described how matter interacted with an invisible medium. Einstein saw something deeper. These equations were not corrections applied to flawed measurements. They were revealing how space and time actually behave. Space-time is flexible, and it reshapes itself depending on motion. From this framework emerged one of the most famous equations ever written. E equals mc squared. Energy equals mass multiplied by the speed of light squared. This equation is often associated with nuclear explosions, but its meaning goes far beyond weapons or power plants. It tells us that mass and energy are not separate things. They are the same substance expressed in different forms. The speed of light squared is simply the conversion factor between them, and it is enormous. Because light speed squared is such a vast number, even a tiny amount of mass contains staggering energy. 1 kilogram of matter fully converted would release more energy than many nations consume in an entire year. Mass is concentrated energy. Energy is dispersed mass. They are not interchangeable only under extreme conditions. They are fundamentally identical. The speed of light appears in this equation not because light is special, but because this speed represents the deepest connection between space and time. That is why the same constant appears throughout physics. In gravity, in particle physics, in quantum theory, in thermodynamics, it has nothing to do with light alone. The speed of light is badly named. It is not the speed of photons. It is the speed at which cause and effect can propagate, the speed at which reality itself updates. Light simply travels at this speed because photons are massless. For more than a century, scientists have tested these ideas with astonishing precision. From atomic clocks to particle accelerators, from satellites to subatomic collisions. Every experiment has reached the same conclusion. The universe enforces this limit absolutely, and anything that tries to reach it pays the price in time, space, and energy. Particle accelerators give us proof every single day. Inside these vast machines, particles are pushed to more than 99% of the speed of light. And as they race through magnetic rings, they behave exactly as Einstein predicted. Their clocks slow down, their momentum swells, their resistance to acceleration rises dramatically. No experiment has ever contradicted this, not once. The speed of light is absolute. Space and time themselves bend to protect it. Relativity is not a hypothesis waiting for confirmation. It is one of the most thoroughly tested frameworks in all of science, verified across more than a century of increasingly precise measurements. And yet, Einstein's theory leaves a deeper question unanswered. It tells us what happens, but not why. Why does the universe have this structure? Why does space time behave this way? Why is the cosmic limit set at exactly 299,792 kilometers per second and not some other value? Einstein showed that this speed is enforced through time dilation and length contraction. But he never claimed to explain why the universe demands such enforcement. That understanding would come later, through quantum mechanics, through new mathematical language, and through a physicist named Richard Feynman, who learned to see reality in a way few others ever could. The answer lies not in engines or particles, but in the quantum nature of existence itself. At the deepest level, reality does not move along a single path. It explores all possible paths at once, and the mathematics governing this exploration makes faster than light motion not merely forbidden, but meaningless, not blocked, not resisted, undefined. The light speed barrier is not a wall standing in the way. It is a boundary beyond which the very idea of motion dissolves. But before we reach that insight, we must understand what happens as we approach the limit. Because the closer you get, the universe reveals impossibility layer by layer, each deeper than the last. Imagine for a moment an impossible spacecraft. Engineers have given you everything physics normally forbids: unlimited fuel, perfect efficiency, engines that never weaken. Your mission is simple: accelerate until you surpass the speed of light. You ignite the engines. Acceleration presses you into your seat as the ship surges forward. The velocity display climbs smoothly. 1% of light speed, 3%, 5. Each second brings clear progress. Each burst of fuel produces exactly the speed increase you expect. At 10% of light speed, you are moving at nearly 30,000 kilometers per second, fast enough to reach the moon in seconds, fast enough to cross continents in the blink of an eye. Yet compared to your goal, you are barely beginning. The engines continue to roar, fuel flows endlessly, the numbers climb: 20%, 30, 40, everything feels normal. The universe seems cooperative. Then you pass 50% of light speed. Something subtle changes. Your engines have not weakened. The thrust feels just as strong. Fuel is still pouring in, but the velocity display begins to climb more slowly. Each additional percentage of speed costs more energy than the last. The clean linear relationship between power and speed has broken. You push harder, more thrust, more fuel. At 60%, progress slows further. At 70%, each gain demands far more effort. At 80%, the curve steepens sharply. By 90% of light speed, the situation becomes surreal. Reaching the next 10% would require more energy than everything you have burned so far combined. Not twice as much, not 10 times as much. The requirement is racing upward toward infinity. You are not fighting friction. Space is empty. There is no air, no drag, no resistance of matter. You are fighting space-time itself, and space-time does not lose. Einstein's relativity explains what is happening inside your ship. As your velocity increases, your resistance to further acceleration increases as well. Early physicists described this effect as a growth in relativistic mass. The faster you move, the harder you become to push. Modern physics uses different language, but the reality is the same. Your momentum is exploding, and with it, the universe is quietly enforcing its deepest rule. Physicists say that your rest mass never changes. You do not become heavier in the ordinary sense, and yet something far more unsettling happens. Your relativistic momentum grows without limit. In everyday physics, momentum is simple: mass multiplied by velocity. But near the speed of light, that simplicity collapses. In relativity, momentum is not just mass times speed. It is mass times speed multiplied by a factor called gamma. And gamma is where everything begins to unravel. Gamma is defined as 1 divided by the square root of 1 minus your velocity squared divided by the speed of light squared. When you are at rest, gamma equals exactly 1. Nothing unusual happens. Newton's physics works perfectly. As you accelerate, gamma begins to rise. At first, slowly, almost politely. At half the speed of light, gamma is about 1.115. Your resistance to acceleration has increased by roughly 15%. You can feel the universe pushing back, but gently. At 90% of light speed, gamma climbs to around 2.3. The same engine thrust now produces less than half the acceleration it once did. You are spending far more energy for far less progress. At 99% of light speed, gamma jumps above 7. Every tiny gain in velocity now costs 7 times more energy than it would at low speed. Your engines are working furiously, but space-time is becoming stubborn. At 99.9% gamma exceeds 22. At 99.99%, it passes 70. Add another 9, and it soars past 200. The pattern is relentless. Each extra decimal place multiplies the cost of acceleration. The closer you get to light speed, the steeper the climb becomes. And at exactly light speed, gamma does not become very large. It becomes infinite, not metaphorically, not approximately, mathematically infinite. To accelerate any object with mass to precisely the speed of light would require infinite energy, more energy than exists in the observable universe, more energy than exists in any finite universe. No engine can supply infinity. No technology can cheat mathematics. This is not a practical limitation. It is a fundamental one. The Large Hadron Collider proves this with astonishing clarity. Deep beneath the border of Switzerland and France, protons race around a 27-kilometer ring at 99.9991% of the speed of light, 7 parts in 10 billion short of the limit. At this speed, each proton carries as much kinetic energy as a flying mosquito. Think about that. A mosquito weighs milligrams. A proton weighs less than a billion billionth of a gram, and yet their energies match. Not because the proton gained mass, but because gamma multiplied its tiny mass into something enormous. Now imagine pushing those protons just a little closer to light speed. The remaining gap is microscopic, but closing half of that gap would require more energy than the collider already consumes. Closing half of what remains would require even more. The curve does not rise gently, it explodes upward. To actually reach light speed would demand infinite power, power that cannot exist. The barrier is not about funding, not about engineering, not about discovering a clever trick. It is written into space-time itself. But energy is only one face of the limit. Time reveals the other. As your impossible spacecraft approaches light speed time, a board begins to behave strangely. This is not a clock malfunction, not a mechanical delay, not an illusion. Time itself slows down. At 50% of light speed, your onboard clocks tick about 13% slower than clocks back on Earth. An hour on Earth becomes roughly 52 minutes for you, noticeable but manageable. At 90% of light speed, the effect becomes dramatic. Your clocks run at less than half the rate of stationary clocks. 1 year on Earth compresses into about 5 months for you. You are aging more slowly than the universe you left behind. At 99% of light speed, time dilation becomes extreme. Your clocks tick at only 14% of normal. For every year you experience, 7 years pass on Earth. Civilizations could rise, transform, and collapse while you complete a single long journey. At 99.9%, your time slows to about 4% of the outside universe. A century passes elsewhere, while you experience only a few quiet years. And as velocity approaches the speed of light, exactly time dilation diverges toward infinity. Time aboard your spacecraft would stop entirely relative to the external universe. This realm belongs only to massless particles. Photons live here. For them, no time passes between emission and absorption. But anything with mass is forever barred. Massive objects can approach the limit endlessly. They can reach 90% of light speed, but they can never arrive, because reaching light speed would require time itself to stop, and for anything with mass, time must always flow. All of these limits reinforce one another, not as separate obstacles, but as a single unified barrier. Energy diverges, time slows toward stillness, and space itself begins to collapse. Length contraction offers yet another window into why light speed can never be reached. As an object accelerates, it does not simply move faster through space. The space it occupies along the direction of motion becomes shorter. This is not physical compression. No force squeezes atoms together. No material is crushed. Instead, the geometry of space changes. At half the speed of light, an object retains about 87% of its rest length along the direction of travel. A 1 meter rod rushing past you would appear only 87 centimeters long. At 90% of light speed, the effect becomes unmistakable. That same rod shrinks to less than half its original length. At 99%, it contracts to roughly 14 centimeters. At 99.9%, only a few centimeters remain. At 99.99%, barely more than a finger's width. The closer the velocity comes to light speed, the faster the contraction accelerates. And at exactly light speed, the contraction becomes complete. The rod would have zero length in the direction of motion, no extension, no thickness along its path. For any object made of atoms occupying three-dimensional space, this is impossible. An object cannot have volume in two directions while collapsing entirely in the third. Time dilation, length contraction, infinite energy requirements. These are not three different walls. They are three faces of the same truth. Space-time itself contains no continuous path that carries massive objects from slower than light motion to light speed, let alone beyond it. The equations do not merely become difficult, they declare such trajectories non existent, and nature agrees. Real experiments confirm these predictions with stunning precision. One of the most elegant confirmations arrives from the sky. High above Earth at altitudes of around 15 kilometers, cosmic rays strike air molecules and create unstable particles called muons. Muons are short lived. Their average lifetime is just 2.2 microseconds. Even moving near light speed, a muon should travel only a few hundred meters before decaying. Classical physics predicts that almost none should survive the long journey down to Earth's surface, and yet detectors at sea level register vast numbers of them. Where do they come from? Relativity provides the answer. At about 99.94% of light speed, a muon's gamma factor is roughly 30. Time for the muon flows 30 times more slowly than it does for us. What appears to be a 50 microsecond journey from Earth's perspective becomes less than 2 microseconds in the muon's own frame. Most of them survive. From the muon's perspective, something equally strange happens. The muon is at rest. Earth rushes upward toward it, and Earth's atmosphere is no longer 15 kilometers thick. Length contraction shrinks it to only a few hundred meters. Again, the muon survives easily. Two perspectives, one reality. Time dilation and length contraction are not competing explanations. They are mathematically identical descriptions of the same space-time geometry. Every day, cosmic ray detectors around the world confirm this result. Particle accelerators confirm it even more precisely. In machines like the Large Hadron Collider, magnetic fields guide protons around circular paths. The strength of those magnetic fields depends directly on the particle's momentum. At relativistic speeds, momentum grows with the gamma factor. If momentum followed classical rules, the magnets would be far too strong or far too weak. The beams would crash into the tunnel walls. Instead, engineers tune the magnets using relativistic equations, and the beams behave exactly as predicted. The collider works because relativity is correct. Even everyday technology relies on this truth. The global positioning system depends on it. GPS satellites orbit Earth at high speeds, causing their clocks to tick slightly slower due to time dilation. At the same time, being higher in Earth's gravitational field makes their clocks tick faster. The two effects do not cancel. Together, they cause satellite clocks to gain about 38 microseconds per day compared to clocks on the ground. Without correcting for this difference, GPS errors would grow by kilometers every day. Your phone would not know where you are. The corrections work perfectly because space-time behaves exactly as relativity predicts. Given this overwhelming evidence, it is natural to wonder whether any loophole might exist. If massive objects cannot accelerate past light speed, could something exist that was already faster? Physicists once imagined such entities. They called them tachyons. Tachyons would always move faster than light, just as ordinary matter always moves slower. They would possess imaginary rest mass, flipping the usual relationship between energy and velocity. For ordinary particles, infinite energy is required to reach light speed from below. For tachyons, infinite energy would be required to slow down to light speed from above. On paper, the idea looks symmetrical, almost elegant. But symmetry in equations does not guarantee the reality. And this is where the universe becomes even more unforgiving. Tachyons create deep contradictions with causality itself. They allow effects to occur before causes. They permit messages to arrive before they are sent. In a universe governed by cause and effect, this is not merely strange, it is fatal. And this realization brings us closer to the deepest reason the light speed barrier exists at all. Not because motion becomes difficult, not because energy runs out, but because beyond this boundary, the very idea of sequence order and causation dissolves. And that is where the story lights next. It is tempting to imagine that the universe might allow two separate realms of motion, one below the speed of light, where all familiar matter exists, and another beyond it, inhabited by exotic particles forever out of reach. Between them, an uncrossable boundary. But the problem is not energy. It is not engineering. It is causality. In the language of special relativity, faster than light motion is mathematically equivalent to motion backward in time. And once time runs backward for even a single observer, the logical structure of reality begins to unravel. Different observers moving at different velocities would disagree about the order of events. For one observer, a faster than light signal might be sent then received. For another, the same signal would be received before it was ever transmitted. A message could arrive before it was created. With that information, the receiver could act to prevent the original message from being sent at all. The cause would erase itself. You could learn the outcome of an event, change your behavior, and thereby prevent the outcome you already knew. You could witness your own arrival before deciding to depart. These are not philosophical curiosities, they are logical contradictions. A universe that permits faster than light communication cannot maintain a consistent order of cause and effect. Information would destroy its own origin. History would rewrite itself endlessly. Every experiment we have ever performed tells us this does not happen. In our universe, causes come before effects. Information flows forward through time. Reality updates itself in a strict and consistent sequence. The speed of light enforces this order. It separates events that can influence one another from events that cannot. It protects causality by preventing any signal from linking space-like separated events. No experiment has ever detected a tachyon. No theory has incorporated them without collapsing into paradox. The overwhelming conclusion is that faster than light particles are not physical objects. They are mathematical ghosts. Quantum mechanics seems at first glance to offer another escape. In the quantum world, particles sometimes appear where classical physics says they should not be. An electron facing a barrier too tall and too thick to cross can suddenly be detected on the other side. This is quantum tunneling. The particle does not climb over the barrier. It does not go around it. It simply appears beyond it. So the question naturally arises. If particles can tunnel through forbidden regions of space, could they tunnel through the light speed barrier itself? Could quantum mechanics bypass relativity? Careful analysis shows that it cannot. Quantum tunneling does not transmit information faster than light. The confusion arises from how tunneling is measured. A quantum particle is not a tiny billiard ball. It is a wave packet spread out in space with a leading edge, a central peak, and a trailing tail. When this wave encounters a barrier, the transmitted portion is reshaped. The peak of the outgoing wave can appear earlier than expected, even before the peak of the incoming wave reaches the barrier. At first glance, this looks like superluminal travel, but information does not ride on the peak of a wave. Information travels at the front edge, and the front edge of the transmitted wave never emerges before causality allows. No signal, no message, no usable information ever outruns light. Experiments in the 1990s tested this directly. Photons were sent through tunneling barriers and their timing measured with extreme precision. Early headlines claimed faster than light motion had been observed, but deeper analysis revealed the truth. The apparent early arrival was caused by wave reshaping, not superluminal transmission. The informational front always obeyed the cosmic speed limit. Relativity remained unbroken. Every apparent loophole closes, not because nature is cruel, but because the universe is consistent. And this leads us to the deepest insight of all. The speed of light is not a limitation imposed on matter. It is the rate at which reality itself can remain coherent. Beyond it, the concepts of before and after cause and effect meaning and sequence dissolve. And that is why the light speed barrier is not merely difficult to cross. It is meaningless to cross it, because beyond that boundary motion itself no longer makes sense. What researchers eventually realized was that these effects were not violations of the light speed limit at all. They were artifacts of how quantum waves behave when measured. Quantum mechanics, strange as it is, obeys the cosmic speed limit just as strictly as classical physics. No signal, no information, no cause ever outruns light. Still, human imagination does not give up easily. Another proposal soon followed, one that seemed to sidestep the barrier without breaking it. In 1994, physicist Miguel Alcubierre introduced a radical idea. What if a spacecraft never had to move faster than light through space at all? Instead of racing through space-time, the ship could reshape space-time itself. In this concept, space would contract in front of the spacecraft and expand behind it. The ship would sit motionless inside a bubble of local space-time, while the space around that bubble flowed like a wave. From the outside, The bubble could move faster than light. From the inside, nothing would ever exceed the cosmic speed limit. On paper, general relativity allows this. Space-time can bend, stretch, and distort in response to energy and mass. Nothing in Einstein's equations explicitly forbids such a geometry. But mathematics alone does not make physics real. The energy required to create such a warp bubble is staggering beyond comprehension. It would require exotic matter with negative energy density matter that repels gravity instead of attracting it. Quantum theory allows tiny amounts of negative energy under very specific laboratory conditions. But the quantity needed for even a small warp bubble would exceed the total positive energy contained in the observable universe, and that is only the beginning of the problem. Later analyses revealed even darker consequences. The front edge of the warp bubble would sweep up particles, radiation, and debris, compressing them into an ever-growing wall of energy. When the bubble collapsed at its destination, that energy would be released in a catastrophic burst powerful enough to sterilize entire star systems. Even worse, the occupants inside the bubble could not control it. Signals from within cannot reach the bubble's boundary faster than light. The ship could not steer slow down or stop once the bubble formed. The Alcubierre drive remains an elegant mathematical curiosity. No known physics allows it to exist as a practical technology. Wormholes offer another tempting idea. In theory, space-time could fold in on itself, forming a tunnel that connects two distant regions directly. Enter one mouth, exit the other light years away, without ever traveling faster than light within the tunnel itself. Einstein's equations permit such solutions. But once again, reality intervenes. To keep a wormhole open and stable, traversable by matter, would require the same impossible ingredient, exotic matter with negative energy density. Without it, wormholes collapse instantly or exist only as microscopic quantum fluctuations far too small for even a particle to pass through. Expanding them to usable size would demand energies and materials far beyond anything nature appears to allow. Every proposed loophole meets the same fate, not because the universe is withholding a secret, but because the secret is already written into space-time itself. There are no paths that connect slower than light motion to light speed or faster motion for objects with mass. The barrier does not exist because something blocks the way. It exists because there is no way on the other side. Einstein showed us this boundary and proved its mathematical inevitability. His equations describe exactly what happens as objects approach light speed. They predict the infinite energy requirement. They match every experiment ever performed. But Einstein did not answer the deepest question. Why does space-time have this structure at all? Why is there a cosmic speed limit? And why is that limit fixed at exactly 299,792 kilometers per second? To answer that, physics had to go deeper beyond relativity into the quantum foundations of reality itself. The explanation would come from a man who did not think in equations first, but in pictures. A physicist who believed nature could be understood intuitively if you asked the right questions. Richard Feynman. When Feynman arrived at Princeton, In the autumn of 1939, he was only 21 years old, but his reputation had already spread. He did not solve problems the way others did. He rebuilt them from the ground up. He trusted insight over tradition. He drew diagrams where others filled pages with symbols. His advisor, John Wheeler, quickly realized something unusual was happening. Feynman was not just learning physics, he was seeing how reality moves. And in that vision lay the true reason the universe enforces the speed of light. Feynman did not approach physics the way most scientists did. Where others saw equations, he saw motion. Where they manipulated symbols, he imagined events unfolding in space and time. To Feynman, physics was not a static collection of formulas. It was a living process. Particles did not merely exist. They moved, explored, interfered, and interacted in ways that could be pictured almost choreographed in the mind. This way of seeing would eventually unlock one of the deepest insights in modern science. Not just what happens as objects approach the speed of light, but why the universe enforces that limit so relentlessly. What Feynman discovered did not add a new rule to physics. It revealed that the light speed limit was never an imposed law at all. It emerged naturally from how reality is built at its most fundamental level. When Feynman began his graduate work, he inherited a theory in crisis: quantum electrodynamics. The theory describing how light and matter interact was mathematically powerful, yet deeply broken. Physicists understood that charged particles like electrons interact by exchanging photons, the quanta of light. They had equations that described these exchanges with remarkable accuracy. But when they tried to use those equations, something went terribly wrong. Consider the simplest possible calculation: a single electron sitting alone in empty space. The electron generates an electromagnetic field. That field contains energy, and the electron must interact with its own field. When physicists calculated this self-interaction using quantum electrodynamics, the answer was not merely large, it was infinite, not approximately infinite, not a value beyond current measurement. True mathematical infinity. According to the equations, every electron should possess infinite energy, infinite mass, and infinite charge. Reality, of course, disagreed. The problem did not stop there. Calculate how a photon scatters off an electron. Infinity. Calculate small quantum corrections to the electron's magnetic behavior. Infinity. Every meaningful question collapsed into the same nonsensical result. To many physicists, this seemed like a fatal flaw. Perhaps quantum mechanics and special relativity simply could not coexist. Perhaps nature itself demanded a deeper framework yet to be discovered. Through the turmoil of the 1930s and the disruptions of war, the problem remained unresolved. Feynman spent the war years at Los Alamos, helping build the atomic bomb even as these theoretical puzzles lingered in the background of his mind. When the war ended and he returned to academic life at Cornell, he attacked the problem with renewed focus and with his characteristic refusal to think the way everyone else did. The resolution emerged almost simultaneously from three different corners of the world: Julian Schwinger at Harvard, Eiichiro Tominaga in Japan, and Feynman himself. Together, though independently, they developed a method known as renormalization. Renormalization did not eliminate the infinities. Instead, it reinterpreted them. When we measure an electron's mass, we are not measuring a bare particle in isolation. We are measuring an electron already immersed in and interacting with its own electromagnetic field. The infinite self energy is already included in the measured value. Rather than calculating that contribution from first principles, physicists could treat the observed mass and charge as fundamental inputs. The infinities were absorbed into quantities fixed by experiment. Mathematically, the theory began working again. Its predictions matched reality with astonishing precision. Philosophically, however, many physicists remained uneasy. It felt like hiding infinities rather than explaining them. Feynman himself was never fully satisfied, and so he pushed further. What he developed next was not just a technical tool, but a new way of thinking about quantum mechanics. He called it the path integral formulation. It later became known as the sum over histories. In classical physics, motion is straightforward. A thrown ball follows one definite trajectory determined by forces and initial conditions. Given enough information, the future is fixed. Quantum reality Feynman proposed is nothing like this. When an electron moves from point A to point B, it does not choose a single path. It explores all possible paths. Every conceivable route, straight curved looping wildly through space-time, contributes to the electron's behavior. Each path carries a quantum amplitude, and these amplitudes combine, interfere, and cancel in precise mathematical ways. Reality at its deepest level is not a single story. It is a superposition of all possible stories. And from this strange quantum accounting, the classical world we experience quietly emerges. In this framework, motion itself becomes something profoundly different, and within it lies the reason the universe cannot allow anything to outrun light. Straight paths, curved paths, paths that twist, loop, and wander far from their destination. Paths that circle stars, drift through empty space, or trace impossible shapes before finally arriving. In Feynman's picture, all of them matter. At first, this sounds almost mystical. How could a single particle explore infinitely many routes at the same time? The answer lies in abandoning classical intuition. In the quantum world, a particle does not travel along a single, well-defined trajectory. Before it is observed, it does not choose one path over another. Instead, it exists in a superposition of all possible paths, connecting its starting point to its destination. Each path contributes something called a probability amplitude. This amplitude is not a simple number. It carries both size and phase, encoding how strongly that path influences the final outcome and how it interferes with others. To predict what we observe where a particle is likely to appear, we do not select one path. We sum over every path. Each possible route adds its amplitude to the total. And because these amplitudes have phases, they can reinforce one another or cancel out completely. This is where classical behavior quietly emerges from quantum strangeness. Paths that wander wildly through space have phases that change rapidly. As you add up their contributions, the phases swing back and forth, positive, then negative again and again. In the end, they cancel almost perfectly. These extreme detours paths that loop through distant regions of the universe contribute virtually nothing to the final result. By contrast, paths that stay close to the classical trajectory behave differently. Their phases change slowly. Neighboring paths remain in step, reinforcing one another instead of canceling. The result is not that the particle is forced to follow the classical path. It is that the classical path is where many nearby quantum paths add together coherently. Classical motion is not imposed, it emerges. Feynman showed that this sum over histories approach produces exactly the same predictions as the traditional Schrödinger equation. Every experiment agrees with both formulations, but the intuition they offer is very different. And for our question, the mystery of the speed of light, this difference matters profoundly. In the path integral framework, the contribution of each path depends on a quantity called the action. The action measures how a particle moves through space and time along a given path. For relativistic particles, the action is built from a function known as the Lagrangian, where space and time are inseparably linked, and the speed of light sets the scale connecting them. Now comes the crucial insight. When a path includes any segment where the particle would move faster than light, the nature of the action changes. It stops being real. It becomes imaginary. This single mathematical shift has enormous consequences. An imaginary action causes the phase of the path's amplitude to oscillate infinitely fast, not rapidly, infinitely. When phases oscillate without limit, their contributions cancel with perfect precision. Every faster than light path interferes destructively with every other such path. The result is absolute. Paths that include superluminal motion contribute exactly zero to any observable outcome. They exist mathematically in the sum, but physically they leave no trace. This is the deepest reason nothing travels faster than light. The universe does not enforce this limit with barriers or prohibitions. There are no cosmic speed signs, no hidden forces blocking the way. Instead, quantum mechanics quietly erases faster than light motion before it can ever appear. Superluminal paths cancel themselves out of reality. Einstein showed us that approaching light speed demands infinite energy and leads to infinite distortions of time. Those infinities hinted at an unreachable boundary. Feynman revealed that why that boundary exists, not because space-time forbids faster motion, but because quantum reality makes it meaningless. There is nothing beyond the light speed limit for massive particles, not a forbidden region, but a realm where contributions vanish, where motion dissolves into silence. The speed of light is not a wall. It is the edge of coherence. And beyond it, reality simply has nothing to say. It does not arrive from the outside. It rises from within the mathematics itself. The way probability amplitudes combine already contains the light speed limit. No extra rule is added. No cosmic boundary needs to be enforced. When the quantum sum is performed, contributions that involve faster than light motion simply erase themselves. They do not survive the calculation. This leads to a profound realization. The speed of light is not a restriction placed on otherwise allowed motion. It is a statement about what motion itself means at the quantum level. Paths that exceed light speed do not fail because they are blocked. They fail because they do not coherently contribute to reality. They cancel out. Asking how to travel faster than light becomes a meaningless question, not because it is forbidden, but because there is no faster than light contribution in the quantum sum that could ever be amplified or used. There is nothing there to work with. To make these abstract ideas calculable, Feynman introduced one of the most powerful tools in modern physics, what we now call Feynman diagrams. At first glance, they look almost childishly simple, a few lines, a few intersections. But behind their simplicity lies deep mathematics. In a Feynman diagram, particles are represented by lines moving through space-time. Interactions appear as points where lines meet, split, or merge. Time is usually drawn flowing upward or sideways. Space extends across the page. An electron emitting a photon appears as a straight line that suddenly branches a wavy line, peeling away as energy and momentum are carried off. The electron continues on, altered by the exchange. Absorption looks like the reverse. A photon line joins an electron line, vanishing into it at a single point. The electromagnetic repulsion between two electrons can be drawn as two nearly parallel electron lines connected by a photon line exchanged between them. Momentum flows from one particle to the other, bending their paths. This simple sketch encodes the quantum origin of electric forces. Each diagram corresponds to a precise mathematical expression. There are strict rules now called Feynman rules that translate every line and every vertex into numbers. To calculate the probability of a process, physicists draw every possible diagram that could contribute, convert each into mathematics, and then add them together. What once required pages of dense algebra became visual, intuitive, and manageable. After Feynman calculations that had taken years of effort could be reproduced by graduate students. The diagrams did not change the underlying physics. They revealed it, and they also exposed something subtle about the nature of quantum interactions. The photons exchanged in these diagrams are not the same as the photons that reach our eyes or strike a detector. They are called virtual photons. A real photon obeys a strict relationship between energy and momentum fixed by its zero mass. Given one, the other is determined exactly. Virtual photons are different. They are not directly observed. They exist only inside the calculation. And because of this, they are not bound by the same constraints. A virtual photon can carry combinations of energy and momentum that would be impossible for a real photon. It can appear to have too much momentum for its energy or too little. It can even momentarily carry negative energy. At first, this freedom seemed dangerous. It appeared to violate familiar conservation laws. But it does not. These apparent violations occur only within the limits allowed by quantum uncertainty and only inside the intermediate steps of a process. When everything is added together, conservation laws are obeyed perfectly. Virtual particles are not physical objects traveling through space in the usual sense. They are temporary disturbances, bookkeeping elements in the quantum sum fixes the mathematics accounts for interactions without ever allowing causality to be broken. And crucially, even virtual particles do not transmit usable information faster than light. The same quantum interference that erases superluminal paths also protects causality here. Nothing escapes the structure. The deeper one looks, the clearer it becomes. The speed of light is not a speed limit imposed by force. It is a coherence limit, a boundary beyond which quantum contributions lose meaning, canceling themselves into silence. And this is why the universe remains orderly, why causes precede effects, why reality updates smoothly one moment flowing into the next, not because it must, but because at the deepest level, this is the only way the mathematics can hold together. At first, many critics dismissed Feynman diagrams as nothing more than clever mathematical shortcuts. They asked how physics could allow particles to momentarily carry impossible energies and momenta. How could such violations appear in calculations and still describe a real universe? Feynman's answer was simple and precise. Virtual particles are not physical objects in the everyday sense. They are not tiny entities flying through space obeying the same rules as particles we can observe. They are accounting tools, ways the mathematics keeps track of how fields interact. The seemingly impossible energies and momenta appear only in intermediate steps. When all possible contributions are added together, these impossibilities cancel out completely. What remains always respects conservation laws, causality, and the cosmic speed limit. This clarification reveals something subtle but crucial about faster than light motion. Within the internal steps of a calculation, virtual particles may appear to travel faster than light. But these superluminal components never survive into anything measurable. They never carry information. They never transmit signals. They never violate causality. Consider two electrons repelling each other. In diagrams, their interaction is mediated by virtual photons. But in reality, if one electron suddenly changes its motion, the other does not respond instantly. The electromagnetic field between them updates at exactly the speed of light. Information about the change propagates outward at the cosmic limit, never faster. This principle extends throughout quantum field theory. Virtual particles may briefly ignore rules that constrain real particles, but observable outcomes never do. Every measurable effect respects the same fundamental boundaries. The machinery of quantum theory ensures that causality is preserved with absolute precision. In this deeper framework, particles themselves are no longer viewed as tiny billiard balls moving through empty space. Instead, reality is made of fields. The electromagnetic field exists everywhere in space-time. When that field vibrates in a particular pattern, we observe the vibration as a photon. The photon is not an object traveling through the field. The photon is the field in motion. The same is true for matter. The electron field fills all of space. An electron is a localized disturbance in that field, not a separate object embedded within it. This perspective explains something that once seemed mysterious. Photons always move at the speed of light because the electromagnetic field is massless. Its wave equation permits disturbances to propagate at only one speed, not faster, not slower, exactly the cosmic limit. Electrons, by contrast, arise from a field that has mass. The equations governing massive fields naturally restrict how fast their disturbances can propagate. An electron may move at any speed, below light speed, but it can never reach it. The heavier the field's associated particle, the more tightly its motion is constrained beneath the light speed limit. This relationship is not imposed artificially. It emerges directly from the mathematics of relativistic quantum field theory. When physicists write down equations that respect both quantum mechanics and special relativity, the speed of light appears automatically. It becomes the maximum speed at which massless influences can propagate and the unreachable boundary for anything with mass. Feynman and others showed that this structure is unavoidable. Any attempt to construct a theory that allows faster than light propagation leads to failure. Probabilities stop adding up. Causality collapses. Logical contradictions multiply. The mathematics simply refuses to cooperate. Only theories in which the speed of light defines the maximum speed of causality remain internally consistent. This is not a rule added to physics from the outside. It is the price of coherence. The universe enforces the light speed limit not by decree, but because without it, reality itself would unravel. At first glance, quantum entanglement seems to challenge this conclusion. Measure one particle, and its distant partner appears to respond instantly, no matter how far apart they are. Einstein famously called this spooky action at a distance and worried it pointed to an incomplete theory. But entanglement does not transmit information faster than light. No signal is sent. No message crosses space instantaneously. Nothing usable travels between the particles. The correlations appear instant because the particles share a common quantum state, not because something moves between them. Causality remains intact. And once again, the speed of light stands unbroken not as a wall, but as the quiet boundary that allows the universe to remain meaningful at all. The connection between entangled particles is undeniably real. When one particle is measured and found to have its spin pointing upward, its distant partner is instantly found pointing downward, even if that partner lies on the far side of the galaxy. At first glance, this seems to defy the cosmic speed limit completely. But the mystery hides in what this connection allows and what it does not. While the correlation appears immediately, it cannot be controlled. When you measure your local particle, the outcome is fundamentally random. Spin up or spin down, each result arrives with equal probability. Your distant partner receives the opposite result, but from their perspective, it is also pure randomness. Nothing about this process allows a message to be encoded. To discover that the results are correlated, both observers must later compare their measurements. And that comparison requires ordinary communication constrained by the speed of light. The correlation exists instantly. The knowledge of the correlation does not. No usable information travels faster than light. Physicists have proven this rigorously through what is known as the no communication theorem. Quantum mechanics permits non local correlations, but it forbids faster than light signaling with absolute precision. Causality remains intact not by accident, but by mathematical necessity. Quantum theory walks right up to the edge of violating causality, then stops exactly at the boundary where violation would begin. Nowhere is the role of the cosmic speed limit more dramatic than around black holes. These objects form when immense mass collapses into a region so small that the escape velocity reaches the speed of light itself. Once that threshold is crossed, escape becomes impossible, not because of a physical wall, but because of causality. The boundary is called the event horizon. It is not a surface you could touch. No membrane, no shell, no barrier of matter exists there. Instead, it is a causal horizon, a dividing line in space-time, beyond which events can no longer influence the outside universe. Light emitted just inside the horizon still moves at light speed, but space-time itself curves inward faster than light can climb outward. The light makes no progress. It remains forever trapped, asymptotically approaching the horizon without ever escaping. To a distant observer, objects falling toward a black hole appear to slow down endlessly. Their light reddens, fades, and stretches. Time dilation grows without bound. From the outside, nothing ever quite crosses the horizon. From the falling astronaut's perspective, however, the crossing happens in finite time. They pass the horizon without noticing anything special, yet in doing so, they exit the observable universe forever. Inside the event horizon, the cosmic speed limit becomes absolute. The singularity at the black hole's center is not a place you can steer away from. It is not down or forward in space. It lies in the future of every possible path. Inside a black hole, moving forward in time means moving closer to the singularity. Escape would require traveling backward in time, and that is forbidden. This reveals something profound. Event horizons are not accidents of gravity. They are expressions of causality itself. The same light speed limit that prevents messages from traveling into the past also seals black holes from the rest of the universe. Causality shapes spacetime, carving out regions that are permanently inaccessible. This idea is echoed in the cosmic censorship conjecture, which proposes that singularities are always hidden behind event horizons, never exposed to the wider universe. If true, it means the speed of light protects reality from its own mathematical breakdowns, shielding observers from the pathologies that occur where gravity level becomes infinite. Black holes stand as monuments to the cosmic speed limit. They mark boundaries. Not even information can cross, no technology, no intelligence, no future civilization, no matter how advanced, can retrieve information once it has passed an event horizon. The speed of light has etched permanent blind spots into existence itself, regions as unreachable as the past. And this is not philosophical speculation. Quantum electrodynamics, the theory Feynman helped perfect, has been tested with extraordinary precision. Its predictions match reality to a degree unmatched by any other physical theory. One of the most sensitive tests involves the electron's magnetic moment, a quantity known as the G factor. Classical physics predicts one value. Early quantum theory predicts another. Neither is quite correct. Quantum electrodynamics adds subtle corrections arising from the electron's interaction with virtual photons in its own electromagnetic field. Each additional correction corresponds to increasingly complex Feynman diagrams loops within loops within loops. Physicists have calculated these contributions to astonishing depth, summing tens of thousands of diagrams. The result agrees with experiment to better than 1 part in a trillion. 1 part but in a trillion. Few measurements in all of science approach this level of agreement. It is overwhelming evidence that the framework Feynman helped uncover is not an approximation. It is a true description of how reality works and why the speed of light stands as the ultimate boundary of causality. Faster than light motion does not exist as a meaningful concept within quantum field theory. This was not a conclusion Richard Feynman reached reluctantly. It was something he seemed to delight in uncovering. Feynman approached physics with a rare combination of playful irreverence and ruthless precision. He once remarked that anyone who believes they truly understand quantum mechanics does not understand it at all. To him, confusion was not a weakness. It was a signal that you were standing close to something fundamental. His path integral formulation did more than simplify calculations. It revealed how quantum mechanics and special relativity interlock so tightly that the cosmic speed limit becomes unavoidable, not enforced, not imposed, inevitable. What appears to us as a barrier is at a deeper level a structural feature of reality itself. Nothing in physics forbids faster than light motion in the way laws forbid certain actions. There is no cosmic rulebook declaring it illegal. Instead, the quantum structure of space-time renders superluminal motion meaningless. There is no path to take, no contribution to reality, no trajectory that survives the quantum sum. This is what Feynman truly uncovered. The speed of light was never a restriction added to motion after the fact. It emerges naturally from how probability amplitudes combine to form the world we observe. Paths that attempt to exceed this speed do not fail. They cancel, they erase themselves before they can influence anything measurable. The mathematics Feynman developed remains the backbone of modern theoretical physics. His diagrams are still drawn daily by particle physicists around the world. His path integral approach underlies quantum field theory, string theory, and ongoing attempts to unify gravity with quantum mechanics. And everywhere this framework succeeds, it confirms the same quiet truth. The speed of light is not the universe's speed limit. It is the universe's update rate, the rhythm at which cause becomes effect, the tempo at which reality refreshes itself. Nothing travels faster because faster has no definition within the quantum machinery from which spacetime itself emerges. Feynman passed away in 1988, having reshaped physics more than once. He contributed to the Manhattan Project, rebuilt quantum electrodynamics, explained superfluidity in liquid helium, anticipated quantum computing decades ahead of its time, and helped clarify the weak nuclear force. Any one of these achievements would have secured his place in history. Together, they established him as one of the defining physicists of the 20th century. Yet his most profound contribution may be this insight that the cosmic speed limit is woven directly into existence at the quantum level, built into the rules governing how possibilities become reality. So, what does this mean for us? If the speed of light is truly the speed of causality, not merely a feature of electromagnetic radiation, then it shapes everything: time, space, history, the structure of the observable universe itself. The barrier is not just a detail of physics, it is the foundation upon which physical reality rests. And despite its name, the speed of light has very little to do with light. This sounds paradoxical until the deeper picture comes into focus. Photons travel at this speed because they are massless, not because the speed belongs to them. Any massless particle moves at this same rate. If gravitons exist, they would travel at it. Gluons propagate at it within atomic nuclei. The constant was present long before the first photon ever crossed the newborn universe. A more honest name would be the speed of causality. It is the maximum rate at which any influence can propagate, the fastest possible connection between cause and effect. Every force, every interaction, every exchange of information must obey it, not because the universe polices violations, but because causality faster than this has no coherent meaning within space-time itself. To see why we must strip causality down to its simplest form. One event influences another. A stone strikes glass. The glass shatters. The strike comes first. The shattering follows. This ordering feels obvious, almost trivial, and yet for it to exist at all, the universe must enforce a deep structure, one that binds time, space, and cause together into a single consistent flow. That structure is what the speed of light truly measures, and it is why the universe can exist at all. Information about the rock's motion must reach the window before the window can respond. The glass panel cannot shatter in anticipation of a rock that has not yet arrived. Cause must come before effect. That connection between cause and effect has to travel through space, and it does so at a finite speed. There is an upper bound to how fast any influence can propagate. Nothing in the universe can carry causation faster than 299,792 kilometers per second. Not electromagnetic forces, not gravity, not the strong nuclear force binding quarks into protons, not any interaction physicists have ever observed or mathematically described. The limit is universal. When you push one end of a rigid rod, the other end does not respond instantly. Your push creates a compression wave that travels through the material atom by atom. In steel, that wave moves at about 5 kilometers per second. For a rod 1 meter long, the far end begins to move a fraction of a millisecond after the near end is pushed. The delay is far too small for human senses to notice, yet it is absolutely real. Even if you imagined a material stiffer than anything we can build, the signal could never outrun light. The speed of sound in any substance must remain below the speed of causality, because sound transmits information, and information cannot propagate faster than cause allows. At first glance, This might feel like an engineering limitation rather than a fundamental law. Perhaps a clever design could bypass it. Perhaps an exotic material could transmit forces instantly. Every attempt to construct such a mechanism collapses into contradiction. The speed of causality is not a wall placed in the universe to restrict otherwise limitless possibilities. It is a defining feature of how reality is structured. Special relativity reveals why this limit is essential for preserving logical cause and effect. Einstein showed that space and time are not separate absolute backgrounds in which events unfold. They are interwoven aspects of a single space time fabric. Observers moving at different velocities do not agree on distances between events. They do not agree on durations between events. These disagreements are not measurement errors or perceptual tricks. They are genuine properties of space-time itself. Some events are connected by cause and effect. Others are not. Events that cannot influence one another are said to be space-like separated. For these events, something remarkable occurs. Different observers can disagree about which event happened first. One observer may see event A precede event B. Another observer moving differently may see B occur before A. A third may judge them simultaneous. This reversal feels deeply unsettling at first. How can the order of events depend on who is watching? Does the universe not have a single objective timeline? The answer is subtle. For events that can causally influence each other, the ordering is absolute. If event A causes event B, every observer, no matter how they move, will agree that A happened before B. Cause precedes effect for everyone. But for events that cannot influence one another, the universe does not define a single ordering. Neither event causes the other. Neither affects the other in any way. The question of which happened first has no absolute answer because it assumes a causal relationship that does not exist. This is where the speed of light becomes essential. Light speed defines the boundary between what can be connected by cause and what cannot. If two events are separated by more distance than light could cross during the time between them, they are space-like separated. No signal, no influence, no cause can link them. If the time between events is long enough for light to travel the distance separating them, the events are time-like separated. A causal chain can exist. Their temporal order is fixed and universal, and events that lie exactly on the boundary where light could just barely connect them trace out the light cone itself. This structure is not a detail of physics. It is the scaffolding that holds reality together. Without the speed of causality, the universe would lose its logical coherence. Effects could precede causes. Information could arrive before it was sent. And the very concept of a consistent history would dissolve. Events whose separation in time is exactly matched by the distance light can travel are called light-like separated. They lie precisely on one another's light cones. A beam of light leaving one event would arrive at the other at exactly the right moment, neither early nor late. This distinction gives space-time its causal geometry. Every event in the universe sits at the tip of two invisible cones, one opening into the past and one opening into the future. The future light cone contains every event that this moment could ever influence. The past light cone contains every event that could possibly have influenced this moment. Everything outside these cones is causally disconnected. It cannot reach you, and you cannot reach it. Right now, your future light cone defines the absolute boundary of your influence. If you were to activate a powerful laser at this instant, its light would spread outward at the speed of causality, carving an expanding sphere through space. That expanding boundary marks the furthest reach of anything you can ever affect from this moment forward. Anything beyond it lies forever outside your influence. Your past light cone tells the complementary story. It contains every event that could have shaped who you are right now. Light from distant stars that entered your eyes altered neural activity in your brain. Cosmic rays from ancient supernovae struck Earth long before humans existed, subtly influencing mutations carried forward through generations. Only events inside your past light cone could have contributed to your existence. Everything else, no matter how dramatic, is causally irrelevant to you. The speed of light determines the opening angle of these cones. If light traveled faster, the cones would widen and more of the universe would become causally connected. If light traveled slower, the cones would narrow, shrinking the domain of possible influence. The specific value we observe gives our universe its particular causal structure. Allowing faster than light travel would fundamentally alter this structure. Events that are currently space-like separated would become causally linked. This is not simply something the universe forbids by decree. It creates contradictions that cannot be resolved within any consistent logical framework. If faster than light motion were possible, you could reach events that lie outside your light cone. But such events do not have a fixed temporal order. Some observers would see them as occurring in your future, others would see them as occurring in your past. By traveling to such an event, you would turn an observer dependent ordering into an objective causal connection. Special relativity shows that this is mathematically equivalent to traveling backward in time. Different observers would disagree about whether your journey moved forward or backward through time. For some, you would arrive before you departed. You would exist at your destination before your journey had even begun. This creates causal loops with no consistent resolution. You could receive information about future events and use that information to prevent them. You could erase the causes that led to the message you received. You could observe your own departure from the standpoint of having already arrived. These are not philosophical curiosities. They are logical impossibilities that shatter the mathematical structure of physical law. A universe that permits faster than light travel is a universe without stable causality. A universe where effects could precede causes, where an information could annihilate itself by preventing its own creation. Every experiment ever performed confirms that our universe does not behave this way. Causality unfolds in a consistent direction from past to future. Causes come before effects. Information flows forward through time and never backward. The speed of light enforces this structure by forbidding causal connections between space-like separated events. It is written directly into the geometry of space-time itself. Physicists describe this geometry using a quantity known as the space-time interval, which combines distance and duration into a single invariant measure. The interval between two events is calculated from the time separation multiplied by the speed of light squared minus the spatial separation squared. This quantity has a remarkable property. All observers, regardless of their motion, calculate the same interval between the same two events. When Einstein first revealed this, it stunned the scientific world because it meant that while space and time could stretch, shrink, and reorder themselves, causality remained absolute. And it is this invariant structure that that quietly, relentlessly, and permanently enforces the cosmic speed limit. The interval itself never changes. All observers, no matter how fast they move or in what direction, calculate the same space-time interval between any two events. They may disagree about how far apart those events are in space. They may disagree about how much time passes between them. But the combined quantity, the interval, remains the same. This invariance defines the geometry of our universe. Space-time does not follow the familiar rules of Euclidean geometry, where distance alone matters, and the Pythagorean theorem applies to space by itself. Instead, it follows Minkowskian geometry, where space and time are fused into a single structure, and a modified version of the Pythagorean relationship governs how intervals behave. Within this geometry, the speed of light appears naturally, not as a property of light, but as the conversion factor linking spatial distance and temporal duration. When we say that light travels at roughly 300,000 kilometers per second, we are really stating a geometric truth about space-time itself. 1 second of time is equivalent to 300,000 kilometers of space within the unified fabric of reality. These are space-time's natural units. An object moving at light speed advances 1 unit of space for every unit of time. In this sense, the speed of light is not a velocity in the everyday meaning of distance divided by time. It is the exchange rate between distance and time themselves. Physicists often simplify their equations by choosing units where the speed of light equals exactly 1. When they do this, the conversion disappears entirely, and space and time reveal themselves as two expressions of the same underlying dimension. Einstein's most famous equation carries this same insight. Energy equals mass multiplied by the speed of light squared. This formula does not merely say that mass can become energy. It says that mass and energy are the same thing expressed in different units. The speed of light squared is the conversion factor that translates between them. Because this factor is enormous, even a small amount of mass corresponds to a staggering amount of energy. 1 kilogram of matter contains on the order of 90 quadrillion joules of energy. Nuclear reactions exploit this equivalence. When uranium nuclei split, only a tiny fraction of their mass is converted into energy. But that fraction multiplied by the immense conversion factor produces the destructive power of nuclear weapons and the controlled output of nuclear power plants. The same principle allows the sun to shine for billions of years. Deep in its core, a small percentage of hydrogen mass is continuously transformed into radiant energy sustaining life on Earth across geological time. The speed of light governs gravity with the same absolute authority. Einstein's general relativity extended these ideas beyond motion and energy to include gravitation itself, revealing that massive objects curve the space-time around them. What we feel as gravity is not a fish pulling across empty space, but motion through a curved geometric structure. When a massive object moves, the curvature it creates must change, and those changes cannot propagate instantaneously. They propagate at exactly the speed of causality. Gravitational waves provide dramatic confirmation. When enormous masses accelerate violently, such as black holes spiraling together and merging, they send ripples through space-time itself, spreading outward like waves across a cosmic pond. Einstein predicted these waves in 1916. Nearly a century later, in 2015, detectors finally became sensitive enough to observe them directly. The signals measured by gravitational wave observatories arrived at detectors separated by thousands of kilometers, with delays measured in milliseconds. From these tiny differences, physicists determined how fast the waves traveled. The result was unmistakable. Gravitational disturbances move at the same speed as light, matching it to astonishing precision, better than 1 part in a million billion. Gravity and electromagnetism share the same propagation speed, not by coincidence, but by necessity. Both are bound by the same causal structure. Both obey the same fundamental tempo of space-time. The speed of light is not owned by light. It belongs to causality itself. It is the maximum rate at which reality can respond, update, and connect one event to another across the vast fabric of the universe. The universe drifts from order toward disorder. This gradual increase in entropy defines the direction of time itself, the arrow pointing from past to future. Yet a profound question remains. Why does entropy increase toward the future and not the past? The equations governing fundamental physics are for the most part time symmetric. Run them forward or backward, and they still work. Nothing in the core mathematics prefers yesterday over tomorrow. So, where does time's direction come from? The answer lies in information and in how fast it can spread. Any small region of low entropy, any pocket of order is statistically unstable. There are vastly more disordered states than ordered ones. Left alone, systems naturally drift toward the configurations that are more numerous. But this drift is not instantaneous. For entropy to increase, information about the system's precise state must leak outward. Correlations must spread from the local region into the surrounding environment. And that spread is limited by one thing: the speed of causality. Information cannot propagate faster than light. As correlations radiate outward at this finite speed, the entropy of the combined system increases. Order dissolves not instantly, but gradually at a rate set by how quickly information can flow. On cosmic scales, the speed of light becomes a governor on the pace of time's arrow itself. Imagine a universe with a much lower speed limit. Informations would spread sluggishly. Entropy would rise more slowly. Structures might persist far longer than they do in our cosmos. Now imagine a universe with a much higher speed limit. Information would flood outward rapidly. Thermal equilibrium would arrive quickly. Stars might burn out too fast. Complex chemistry might never stabilize. Life might never gain a foothold. We appear to live in a universe balanced delicately between these extremes. A universe where stars can shine for billions of years, where planets cool gradually, where chemistry has time to grow complex, where life can emerge, adapt, and evolve before entropy finally claims everything. This may not be accidental. The anthropic principle offers a modest explanation. Observers can only exist in universes whose fundamental parameters allow observers to exist at all. Universes with radically different causal speeds may never form stars' planets or stable structures capable of supporting awareness. We observe this speed of light because it is compatible with our existence. That in its own size explains why we are not surprised by the value we observe, but it does not explain why the universe chose this value rather than another. That deeper question remains unanswered. Fundamental constants. The speed of light, Planck's constant, the strengths of forces appear finely set. Physics can describe how they shape reality, but not yet why they take the values they do. The speed of light reaches into quantum mechanics in subtle ways that extend beyond even Feynman's insights. Werner Heisenberg's uncertainty principle sets hard limits on what can be known simultaneously: position and momentum, energy and time. These limits are not technological shortcomings, they are built into the structure of reality. And when energy and momentum are related in a relativistic universe, the speed of light becomes the essential bridge between space and time. In relativistic quantum mechanics, uncertainty itself depends on the same conversion factor that unites distance and duration. Remove or alter that factor, and the theory collapses. Quantum field theory, the framework that unites quantum mechanics with special relativity, only works when all fields respect a single maximum propagation speed. Attempts to construct quantum theories that permit faster than light signaling fail catastrophically. Probabilities become nonsensical. Negative values appear where none can exist. Conservation laws break. Causality loops back on itself. The mathematics refuses to hold together. Again and again, physicists discover the same result. Only theories that enforce the speed of light as the ultimate limit remain logically consistent, not because the universe enforces a rule, but because any universe that violated it could not coherently exist at all. This is not an extra rule layered onto physics. It is the inevitable result of demanding that the theory make logical sense at all. The quantum nature of matter and the relativistic structure of space-time lock together only at one specific cosmic tempo. Change that tempo, and the entire framework unravels. Some speculative ideas suggest otherwise. A few theorists have proposed that the speed of light might vary across cosmic history. Perhaps it was higher in the earliest moments after the Big Bang. Perhaps it differs in distant regions of the universe. These variable speed of light theories attempt to solve certain cosmological puzzles without invoking cosmic inflation. If true, they would revolutionize physics. But extraordinary claims require extraordinary evidence. Physicists have searched relentlessly for any sign that light's speed depends on direction, location, or time. Laboratory experiments test its isotropy with extreme precision. Astronomical observations compare light arriving from distant galaxies across billions of years. So far, every measurement agrees. Within the limits of our instruments, the speed of light is constant. If even a tiny variation were confirmed, the consequences would be enormous. Fundamental constants would no longer be constant. Quantum field theory would require reconstruction. Modern cosmology would need to be rewritten from the ground up. The implications would ripple through every branch of physics. For now, the verdict is clear. The speed of light stands as humanity's ultimate boundary. It defines how far we can reach, how fast we can travel, and how widely we can communicate. No technology consistent with known physics will ever carry humans to distant galaxies within a human lifetime. Our nearest large galactic neighbor, Andromeda, lies more than 2 million light years away. Even at 99% of light speed, a journey there would take 2.5 million years as measured on Earth. Time dilation would soften the passage for travelers, but the price would be irreversible. They would return to a world unimaginably old. Everyone they knew would be long gone. Civilizations would rise, fall, and vanish in their absence. Even interstellar travel within our own galaxy faces sobering limits. The nearest star system, Alpha Centauri, is over 4 light years away. A spacecraft traveling at 10% of light speed, far beyond any propulsion system we can realistically imagine, would take more than 4 decades to arrive. By the time the crew returned, their world would no longer be the one they left. Communication obeys the same constraint. A message sent to another galaxy would take millions of years to arrive. A reply would take millions more. Meaningful conversation across such distances is impossible even in principle. The universe isolates its civilizations not by walls of matter, but by the finite speed of causality. This isolation grows stronger with time. Cosmic expansion carries distant galaxies away faster than light can bridge the growing gap. A signal sent today toward a galaxy 10 billion light years away will never arrive. That galaxy is already slipping beyond our future light cone. We are not necessarily alone in the universe, but we are causally alone. Yet the same limit that isolates us also protects us. Without a universal speed of causality, the universe would collapse into contradiction. Effects could precede causes, information could flow backward through time. Logical order would dissolve. Our ability to think depends on causality. Signals in the brain must arrive in sequence. Memories must record the past, not the future. Perception must follow stimulus. Consciousness itself relies on a stable temporal structure. A universe without a cosmic speed limit would be a universe without coherence. Richard Feynman understood this at a profound level. His path integral formulation revealed that faster than light contributions cancel themselves out before they can affect reality. His diagrams encoded causality directly into the mathematics of particle physics. Again and again, his work showed the same truth. The barrier is not a wall blocking passage. It is a structural feature of existence. There is no other side to break into because faster than light motion is not a meaningful concept within the mathematics that describes reality. Asking how to exceed light speed is like asking how to walk north of the North Pole. The question assumes a destination that does not exist. You are reading these words in a universe governed by constraints we did not choose and cannot escape. The speed of light marks the boundary of causality, the geometry of space-time, the ultimate reach of thought action and influence. Nothing we build can bypass it. Nothing we discover can erase it. It is woven into reality more deeply than matter, more deeply than energy, more deeply even than space and time. The speed of light is not a restriction imposed on the universe. It is what allows the universe to exist at all. It is the tempo at which reality updates, the frame rate of the cosmos, the silent rhythm beneath everything from quantum fluctuations to colliding galaxies. Feynman spent his life uncovering how this rhythm emerges from the deepest principles of physics. And in doing so, he revealed that the universe is not limited by light speed, it is defined by it. His work revealed something quietly profound. The cosmic speed limit was never an added rule imposed on the universe. It was always the natural outcome of how quantum fields and relativistic space-time interlock. The universe does not forbid faster than light travel. Rather, it is built from elements for which faster than light motion has no meaning at all. There is no prohibition because there is nothing to prohibit. No hidden door, no forbidden corridor, just the structure of reality complete as it is. And so we live within absolute boundaries. Our past light cone contains everything that could ever have shaped us, every star whose light reached Earth, every event that influenced the chain of causes leading to this moment. Our future light cone contains everything we can ever affect, every signal we might send, every action whose influence can still spread outward. Beyond these cones lies most of space-time itself, vast and silent, causally disconnected. Regions we can never reach, events we can never witness, places that will forever remain untouched by our presence. This is not a failure of the universe, it is the cost of coherence. Without a universal speed of causality, reality would collapse into contradiction. Effects would precede causes. Information would undo itself. Time would lose its direction. With this limit, something remarkable becomes possible. Stars can burn steadily for billions of years. Planets can cool. Chemistry can grow complex. Life can emerge. And minds can arise that are capable of asking why the universe works the way it does. The speed of light is the universe's metronome, the steady rhythm that sets the pace of existence. Every photon, every gravitational ripple, every vibration of every quantum field moves to this same beat. The universe cannot speed it up, because the rhythm is not separate from the universe. The rhythm is the universe. Einstein showed us how this structure works. Feynman showed us why it must be this way. Together they revealed a quiet truth. This limit is not a cage, it is a foundation. The ground beneath all matter, all energy, all thought exists because causality flows in one direction at one maximum speed through the unified fabric of space-time. The boundary that confines us is the same boundary that makes us possible, and to understand that boundary is to touch the deepest insight physics has ever offered about what it means for anything to exist at all.